Alright, so this is exercise 9.1. In this exercise we're given this dynamic system on state space form, and task A is to calculate a state feedback that places the poles of the closed loop system in two different cases here. So in the first case we're going to place them in -3 and -5, and in the second case we're going to place them in -10 and -15. And then we'll discuss the difference between these two cases. Okay, so first of all I'm just going to name these matrices as we usually do. So this one is A, and this one is B, and this one is called C. And now we're going to use state feedback, which means that the input will be selected as -L times X plus a reference signal. So let's call it yref. And since we have two states in our system, this L matrix here will just be a row vector with components L1 and L2. Okay, so what we're going to do is simply to substitute u up here with this feedback expression. So let's do that. That's going to give us x dot is equal to ax plus b times -lx plus yref. This is equal to ax minus blx plus byref. So let's now do a Laplace transform of this equation here. So here we have a time derivative. So when we Laplace this, we have to multiply it with s. So we'll get s times x of s is equal to a times capital X of s minus bl x of s plus b yref of s. Okay, so we want to solve this for x, so let's move over the x terms to the left hand side and then factor it out. That will give us s times identity matrix minus a and then plus bl times x of s is equal to just b times yref of s. And now we can solve this for x by multiplying with the inverse of this matrix here. So x of s is going to be equal to s times I minus a plus bl inverse times b yref of s. And now we just note that y is equal to c times x. So in order to obtain y here, we just multiply with x of s, which is of course just this thing. So y is equal to sc times si minus a plus bl inverse times b yref of s. So this is the closed loop system. We have the reference signal here and we have the output here. And of course this thing is then equal to the closed loop transfer function gc of s, which we can write as a fraction with the numerator. Let's call that a of s, and the denominator, let's call that one b of s. So what we're interested here in is b of s, since we want to make a pole placement, and a of s is actually not even affected by state feedback, so we don't have to care about that one. Alright, so let's find out what bs is. So since we have, oops, it's a bit tilted. So since we have an inverse here, bs will just be given by the determinant of this matrix that we invert. So it's determinant of si minus A plus BL. Alright, so let's calculate that one. So this is the determinant of what? So let's write this out explicitly. So the first one is just SS 0, 0, S times the unit matrix, and then it's minus A, and A was equal to what? A was equal to minus 2, minus 1, 1, 0. And then we have plus BL. So let's go down here. As you see, B is just a column vector 1, 0, and L is just L1, L2. So B times L is just going to be L1, L2, 0, 0. Alright, so let's move on with this. So what is this going to be? Well, let's start, do this element by element. So this first element will have S minus minus 2, which is plus 2. And then we'll have plus L1. And for the second element we'll have 0 minus minus 1, which is just plus 1. And then plus L2. And for this element we'll have 0 minus 1, so that's minus 1, plus 0, so that's just going to be minus 1. And for the last one we have S minus 0, and then plus 0. So it's just going to be S. So we'll just need to take the determinant of this matrix. And it's a 2 by 2 matrix, so the determinant is obtained by taking the product of the diagonal elements and then subtract the product of the anti-diagonal elements. So this is equal to S plus 2 plus L1 times S minus minus 1 times 1 plus L2, which is equal to S squared plus 2 plus L1 times S, and then plus, because we're minus minus, plus 1 plus L2. Alright, so now we had two different cases. In the first case we were asked to place the poles in minus 3 and minus 5. So that means that the desired pole polynomial Bs should be equal to S plus 3 times S plus 5. Since here we have a pole in minus 3 and one in minus 5. And this is equal to S squared plus, let's see, 5 plus 3, which is 8, S, and then plus 15. So if we compare these two expressions, we'll see that we must have 2 plus L1 should be equal to 8, and 1 plus L2 should be equal to 15. And this is quite simple equation system, so it will give us that L1 is equal to 6 and L2 is equal to 14. And the resulting control law in this case will be what? Well, it's minus, as you remember, minus Lx plus y ref. So here it's simply minus 6x1, minus 14x2 plus y ref. Alright, so in the second case we were asked to place the poles in minus 10 and minus 15. So then the pole polynomial will be given by s plus 10 times s plus 15. So in this case, the desired polynomial is going to be s squared plus 25s plus 150. So the equation system in this case will be 2 plus L1 should be equal to 25, and 1 plus L2 should be equal to 150. And the solution here is that L1 is equal to 23 and L2 is equal to 149. So the control law in this case will be that u is equal to minus 23x1 minus 149 x2 plus y ref. Okay, so let's compare these two situations. Well, in the second case we place the poles further away from the origin, and that means that this system will be faster than this one. But in the same case, we see when we compare the controllers here that we have much higher coefficients in this second case, which of course puts some more demands on the system itself, because in a physical system x1 and x2 represents some physical quantities, and here we have to select the input signal, and we have to, when we multiply these quantities with such high numbers, the input to the system will be quite large. And I mean, depending on what these states represent, that may be a challenge, or it may be even impossible to use such high values, because there's always a bound on what input you can use in a physical system. So in theory this is better because it's faster, while at the same time we must remember that in a physical system we always have limits on the input. Alright, so let's move on to task B. And in task B, we're given that suppose that only the output is measured. Calculate an observer that makes the transfer function from the reference signal to the output the same as in A. Discuss the influence of the poles of the observer. Okay, so we can't measure the states, so we need to estimate them. And then we're using an observer, so that's why we denote with this x hat. So the equation for the observer is pretty similar to what we had before, but we also have this term at the end here, which is an observer gain k times y, the output, minus c times x hat. So this term is a measure on how good our estimation is. If our estimation is perfect, then this is going to be equal to 0, since y is equal to c times x. So if x hat is equal to x, which is what we want, then this thing is going to disappear. So this observer gain here, k, is just a column vector with two components, because we have two states. So k1 and k2. And our task now is to determine these values of k1 and k2. Alright, so let's take a look at the estimation error. So the estimation error, we call that x tilde, is just the difference between the observer and the true state. So what is that? Well, we have equations for the time derivatives of these things here, so let's use that. Let's just plug in these dots here. So this observer is given by this equation here, a x hat plus b u, put out the argument, plus k times y minus c x hat, and then we subtract the true state, and true state is given by ax plus b u of t, this, and this is equal to a, so we have a there and there, so we have ax hat minus x, and we'll see that we have b times u here and we have minus b times u here, so u is going to disappear, so let's not care about that one. Then we have plus ky minus kc x hat, and we can identify this difference. It's just x tilde, so we have ax tilde plus k times y, but then we're going to make use of the fact that the output y is just equal to c times x, so it's kcx minus kcx hat, and of course, oops, we can write this as kc times x minus x hat. So what is this? Well, this thing is equal to x tilde almost, what we've just flipped the positions here, so this is minus x tilde, so this thing is equal to ax tilde minus kc x tilde, which is a minus kc x tilde. So if we just summarize this, you see that x tilde, the derivative of x tilde is equal to a minus kc x tilde. So this is just a differential equation. So what we have to do here is to place the eigenvalues of this matrix in the left half plane, and then we'll know that this error will decay towards 0. And the further away from the origin that we place these eigenvalues, the faster will this error decay. But it will also make the observer more sensible to noise. So that's a trade-off that you're making when you're designing the observer. So that will give us a characteristic equation very similar to what we had when we did state feedback in the previous task. So let's calculate this determinant. So this is equal to what? Well, the only difference here, except as compared to before, is that we have plus kc instead of plus bl. So this shouldn't be hard. So a was equal to minus 2 minus 1 1 0, and then kc is equal to what? Well, c was just equal to 1 0, and k is equal to k1 k2, so that's just gonna be k1 k2 0 0, like this. So let's continue here. So we have the determinant of so once again, let's do this element-wise. So first it's s minus minus 2, s plus 2, plus k1. And then for the second element, it's 0 minus minus 1, which is plus 1, and then it's plus 0. So it's just 1. And then we have 0, -1, plus k2, which is -1 plus k2. And then for the last element we have s minus 0 plus 0, so it's just s. So the determinant is going to be s plus 2 plus k1 times s minus 1 times -1 plus k2, which is equal to s squared plus 2 plus k1 s minus 1 is plus 1, and then minus k2. Alright, so the next thing we have to do now is decide on where we want to place the poles of this observer, and that's up to us. But a rule of thumb is that we should place these poles of the observer such that the observer becomes faster than the closed loop system. So the idea there is that if we don't have a good estimation of the states, then it's going to be hard to do control. So in order to make the control efficient, we want this estimation error to decay at least as fast as the dynamics of the system. So in task A, we place the poles. We had two different cases, but in the last case we placed them in -10 and -15. So if we consider that case, we would like the poles of this observer to be further away from the origin. So let's say that we place them in -20, for instance, both of them. And that would correspond to what? Well, of course, let's write it to 2 poles in -20 gives what equation? Well, then we'll have s plus 20 squared, which is equal to s squared plus 40s plus 400. And if we demand that this should be equal to this expression, then we'll see what we have to select for k1 and k2. So the equation system will be 2 plus k1 is equal to 40, and 1 minus k2 is equal to 400. Okay, so this is easy to solve. K1 will be equal to 38, and K2 will be equal to minus 399. So where we place the poles of the observer is a design choice, but remember what I said earlier, that we can make the error decay arbitrarily fast. So if we place the poles very far from the origin, the error will decay fast, very fast, but at the same time it will make the observer more sensible to noise. So that's a trade-off that we have to remember.